Hello students, so welcome to this new course by me, biomolecular spectroscopy. You know, spectroscopy is one common stream or subject that is favorite to all the disciplines, say starting from a physicist, also for chemist and for biologist. The concept of a spectroscopy remains same, but molecule under investigation can vary. Physicists typically like to look at small atoms like for sodium atom, rubidium atom and all those small atoms and look at in detail the property of these atoms or some molecules. Chemist likes to have like to look at the molecules like organic, inorganic molecules, chromophore, fluorophore and all those. And biologists use same chromophore, fluorophore in context of biological molecules, say DNA, protein, nucleic acid, hemoglobin, many of such things, and they like to connect these concepts to life science and want to understand the phenomena that are associated with life science or daily life. Now, that is the uniqueness of a spectroscopy. It is flowing from physics to chemistry to biology, and therefore, it becomes very relevant subject. Many questions in biology are actually dealt with concept of a spectroscopy. So, looking at the molecule inside the cell or inside a tissue or inside an organ, all those places spectroscopy remains a constant theme, and therefore, understanding spectroscopy is of paramount importance. So, essentially what is spectroscopy, we can say it is a theory of absorption of light by a molecule, right. So, it is nothing but a light matter interaction. Any sorts of electromagnetic wave or light when interacts with a molecule and gives certain rise of property, that is what we look at this in the spectroscopy. So, propagation of electromagnetic wave through space and their interaction with the matter actually is the crux of spectroscopy. So, you see the basic concept of spectroscopy. What is a spectroscopy? Actually, we can start. So, spectrum measurement is the subject where which can be defined as a spectroscopy. Spectrum measurement. What is a spectrum? Spectrum is nothing but like a pattern of a light, right. In Hindi it is called varnakram, and a spectroscopy is varnakram. So, varnakram mapi or varnakram mapna in Hindi is a spectroscopy, or in Sanskrit you can say the varnakram mapna is a spectroscopy. Varnakram is a pattern of a light or pattern of a color. So, seeing the world is a spectroscopy, right. Whatever we see, we perceive the world via interaction of visible light with the light receptor in our eyes, right. So, if you are looking a molecule like looking at apple or looking at green leaf, we are perceiving this world of nature when some light is coming to our eye and it is falling on receptor and we are making some image in the brain. That is what we can call it a spectroscopy. That is as simple as that, right. So, say every day how we are doing it, light in every day. So, you look at the sky, why sky is blue? We know some phenomena gives the color of sky which says it is a blue, or in cloudy it looks white. Similarly, why does spinach look green, or why does the sunglass block the glare? So, there is a something that is happening between light and matter, right. So, this is phenomena that we have studied in our high school. So, when a light shining on an object, it can selectively absorb, right. So, light selectively absorbs or scatter light. Here some scattering happening, some absorption and whatever is reflected. This is something reflecting. So, our goal is to understand this fundamental principle behind everyday phenomena that is happening in this course of spectroscopy, right. Now, look at this picture. What do you see here, right? Something is happening here, sun is either setting or rising. how can you identify whether sun is setting or rising? Is this information good enough? Suprabhat hai ya Shubh Sandhya hai? You cannot say. Here what is happening? Can you say whether sun is setting or sun is rising? But something is, you can see many colors here happening, right? The sky is blue, the cloud is white, here the sun is reflecting some orange, red color, and all those are happening. That is what we are perceiving through our eyes, that is the color is happening. But to delineate whether sun is setting or rising, you need another information, right. So, therefore, even in this simple phenomena of sun setting or sun rising, right, in the previous picture we have one picture of sun either setting or rising, in another we have another picture, right. But even to distinguish whether sun is setting or sun is rising, if we are only given this picture and we are perceiving this picture and want to delineate what is happening, we were unable to clearly distinguish whether sun is setting or rising. So, you require another information or another dimension to clearly say what is happening, right. So, therefore, in this spectroscopy there is not one kind of a spectroscopy, there are many kind of information that brings the complementary information to tell about a phenomena that we perceive in everyday's light. Here clearly you can say what all is happening. There is a sunlight falling on an apple, right, and some signal is coming and coming to our eyes, right, and in from the eye there are receptor, right. So, rhodopsin receptor or whatever receptor in eye, that gives some image and that is made in the image, and by looking at this image we can say that this apple is looking red, right. So, reflected or transmitted through object to our surrounding. How much and what spectral region are absorbed depends upon the atom or molecule, whether this apple is absorbing light or reflecting light. This is the phenomena happening in here. So, there is something here which upon interaction with the sunlight is reflecting or transmitting light, and that is what we are perceiving through our eyes, and that is what we can call it is a reflectance or the absorbance, and this gives us light information that it is a red, right. Right. So, what we learn from here, what we all need to do an spectroscopy or to investigate, one is sunlight, right, sunlight which is the source of a light. Sun is shining some light on an object, so you require an object, and then you require a detector. Here is my detector, right, receptors in the eye is a detector, and then you require some data processing devices which is in our brain, and together we can call these phenomena that we are seeing is an spectroscopy. So, what we need? A light source, it can be a sun. In our lab instrument it can be a different kind of lamp. Then we require an object, like in previous slide we had an apple. So, an object which can reflect or which can transmit, scatter or absorb light. So, one of these phenomena this thing should do. So, we require a light source, we require an object, and third thing an receptor. So, a receptor in our eyes, and in the instrument like a physical spectrometer we require a detector which detects. So, wavelength dependent detector that should be, in this case when we are looking at the apple, it is a detector in our eyes. In the instrument case you have to have a detector. So, this total apparatus we can call a spectroscopy study is a spectrometer. The instrument that measures the spectrum is called a spectrometer, and the plot of that particular property of the matter against the wavelength or frequency or energy of radiation is called a spectrum. So, when we are plotting the phenomena of this interaction against some wavelength or a frequency, it is called a spectrum. So, the instrument that measures the spectrum is called a spectrometer, and the whole phenomena of this study is called spectroscopy. Spectroscopy is nothing but the phenomena of measuring the spectrum. Spectrum is coming from this light matter interaction and detected through one detector, right. So, that is what spectroscopy is. So, spectroscopy also means the dispersion of light into different component of the color. So, this you have done in your high school or even primary elementary school. Here is a sunlight falling on a prism and you can see the 7 colors, right. So, 7 colors are splitted by this light. This is the spectrum and you know what is the wavelength, the blue to like a red. Here the frequency and wavelength are arranged in a particular order. These 7 colors originate from the sunlight, right. So, similar thing we have seen in the phenomena when this rainbow or Indradhanush may, after like a rainy season you might have seen in sky there is a Indradhanush coming up where also you see 7 colors. So, this 7 color is splitting from the sunlight. That means, sunlight is a mixture of different wavelength of these lights starting from ultraviolet or say violet, VIBGYOR to red or infrared, right. So, that is what we see. And that is interesting phenomena I just want to connect to you. We all know that sun god has a 7 horse, right. So, 7 horse and what you see, sunlight is splitting into 7 colors. So, sun, people have perceived this concept of 7 colors and they depicted in their literature by these 7 horses. So, if you look at somewhere like in the Sanskrit text it is written Sapta Aswam Rath Arudham, right. So, Prachandam Kashyap Atmajam, you don't go to all those details, but it says that sun is coming on Saptaswa, 7 घोड़ों पर सवार, घोड़ों के रथ पर सवार होकर हे सूर्य प्रचंड सूर्य आप आते हैं. So, that clearly says that the 7 color phenomena that we see through prism or through rainbow is a concept that people appreciated much before the prism experiment was done. It is just observational science like made them believe that sun has 7 colors. Otherwise, the Sapta Rasva could have been Ashta Aswa or Navam Aswa, but here exactly 7 horses are depicted. It clearly says that there are 7 frequency that can be seen by human eyes and that is what they have perceived it, right. So, now what we can summarize the study of interaction of electromagnetic radiation with the matter, we can call it spectroscopy. Now, as you know from other courses or your high school knowledge or even the graduation knowledge, that electromagnetic radiation can be classified into wave and particle. This is called wave particle dualism, and spectroscopy essentially is the interaction between this matter and particle. Like particle, what are the particles in this electromagnetic wave? It is a electron or neutron. So, electron or neutron interacts with a matter, that also gives some kind of a spectroscopy. Like here the X-ray diffraction, X-ray particle diffracts with matter. Like when you go to hospital and by playing football your bone is suppose broken and doctor says you go and get an X-ray diffraction done. So, you go to doctor and doctor recommends to some pathology lab where you put your leg and X-ray beam is shined and you can see a crack in your bone. So, that is again a spectroscopy. Here particle is interacting with the matter that is in your leg, right. Similarly, you see neutron scattering happening, electron microscopy is happening or NMR spectroscopy. These all are different kind of spectroscopy. Or you can say wave interacting with the matter like UV visible spectroscopy, UV light or visible light that interacts give to something called UV visible spectroscopy. So, we are going to study this spectroscopy in this course. Also fluorescence, when the molecule absorbs light and emits certain kind of light, that is called fluorescence, we are going to also study this. Then this circular dichroism, a circularly polarized light interacts with the matter and then gives differential absorption, that is called circular dichroism, we are going to study. Raman and infrared, this works when infrared radiation interacts with a matter and gives the property, that is called Raman spectroscopy or infrared spectroscopy. In this course we are not going to deal with NMR spectroscopy and mass spectroscopy. There will be a specialized course for both of these, but all these spectroscopy, UV visible, fluorescence, CD, Raman, infrared, NMR, mass spectroscopy are extremely crucial when we want to understand the structure and dynamics of a biomolecule. Therefore, not one technique, but a multiple technique, as I was giving you analogy of sunset and sunrise. Similarly, these biomolecule, to understand the structure and dynamics of biomolecule, not one technique, but a series of these techniques will be required, because they give a complementary information, and that is how we can study the structure and dynamics of a biomolecule, right. So, what till now we have studied, I came back to the same slide. The spectroscopy is all about seeing. Seeing is a spectroscopy, and we perceive the world via interaction of visible light with the light receptor in eyes. In this case, since we cannot look at biomolecule with our eyes, therefore, we require fancy detector and we require fancy light source. Biomolecules are very tiny, right. If you know nano size or micro size, micrometer size, those are there. We cannot see and distinguish them with our naked eye. We require a powerful detector system, and therefore, the biomolecular spectroscopy is nothing but a simple spectroscopy concept, where we want to see and perceive these tiny molecules through the light matter interaction concept, right. What are some of the objectives that we can look at and how you can perceive it? So, when you say you have gone to pathology lab, right, and you are visiting a clinic, and you see a nurse is measuring the glucose with a drop of a blood in a second, right. How do that? It pricks just a needle and it puts blood on the slide, right. And then what they do? Blood glucose device rely on how sugar molecule absorbs the light with a specific wavelength, convert that invisible molecular word into instant and actionable medical information, and then you know somebody's blood glucose level is this much, right. So, otherwise, unless until we do this test where we examine the blood glucose level using the spectroscopy concept, we do not know how much sugar it has and what is the status of your blood. So, spectroscopy essentially empowers us to see and measure the molecule that is so tiny, right, from the traditional microscope, and watching how they interacts with the light, we can make the invisible visible light, and then that has revolutionized the diagnosis, research and daily life. So, that is the connection of spectroscopy in the medical field. Here, using a one drop of blood, you can understand the blood parameter. So, coming back to the concept of light matter. So, you know light propagates like this, EM wave, electromagnetic wave. So, this is electrical dimension, this is the magnetic dimension, and this is the direction of propagation. And there are few concepts that you might have studied. This light has wavelength, it has a frequency, and it has a speed, and that is connected by C is the speed of light, frequency and wavelength, right. So, light, we know it is a electromagnetic wave, and that electromagnetic wave interacts. So, we have already seen electromagnetic wave has two natures, the wave nature and the particle nature. For wave nature, since it is propagating in a particular dimension, it should have a wavelength, right. This is the wavelength. Then a frequency, how fast up and down it goes, frequency, that is measured in hertz, wavelength is measured in angstrom or nanometer, and then the speed, and that is the speed of light is c. So, you can just put an analogy, right. When you go and sitting just quietly on the pond, and you are seeing some ripples are propagating here, that is a ripple are propagating wave nature, or just you put a conker in the still water, you see ripples are coming, that is a wave nature of the light. So, you can see clearly, and there is a amplitude coming up and down, there is a wavelength that is happening. So, that is how wave propagates, but since this is the wavelength or frequency is so tiny that we cannot see from eye, well, that is what is wavelength. From top of this to top of this is wavelength, and that is the electric component. perpendicular is a magnetic component and this is the propagation in the light, right. So, electromagnetic radiation can be defined as a wave as well as the particle. And for wave, what we had here, the important component is your frequency, your wavelength and speed. For the particle, you have like a particle which is called a photon. So, here is a like a frequency and this is Planck's constant. So, energy associated can be given h mu, and intensity or brightness of the radiation depends upon the number of photon. So, a wave nature of the light we can use in various spectroscopy like UV visible spectroscopy, IR spectroscopy, fluorescence spectroscopy, so and so forth. Particle nature, right, we look at diffraction, neutron diffraction, electron diffraction and all those, right. So, wave nature, electromagnetic wave as we were mentioning, it has two component, an electric component and magnetic component. It oscillates with the same frequency that are oriented perpendicular to each other. Frequency of the wave is mu, wavelength is lambda, and that is the connection with the speed of the light. Frequency and wavelength are often used to characterize the electromagnetic wave. So, you remember we were talking the 7 colors in the light. So, blue and red, blue comes first, red comes later. So, what is the wavelength of a blue? Around 300 say nanometer, and 700, 750 for red. So, the frequency, if the wavelength is less, frequency is more, and if wavelength is more, frequency is less, because they are connected using this concept, right. So, mu higher, lambda lower, and vice versa, right. So, the another concept that we will come across when we are dealing with IR spectroscopy, this mu bar will be called wave number, that is a reciprocal in centimeter. So, 1 by lambda is mu bar. So, here you can see C equal to mu lambda, C is speed of light, centimeter per second or meter per second, mu is frequency in hertz, that is per second, lambda is in like a centimeter, nanometer, meter. Here the wavelength wave number is 1 by centimeter inverse and lambda is in centimeter. So, wave number is mainly used in vibrational spectroscopy. Otherwise, in all other spectroscopy we use the frequency or the wavelength. Now, when we are talking about the particle nature of the electromagnetic wave, you have to say particle nature of electromagnetic wave is essentially light as a particle. Light as a particle we can call it photons, this you have studied in your basic physics. So, quantum nature says that they are quantized. So, wave light travels as a wave and absorbed or emitted in a discrete pocket of energy, that is called photon or a quantum, right, and that is a Planck's relation. So, you can have energy of a single photon E that is directly proportional to the mu and inversely proportional to the lambda, E equal to h mu or E equal to h c by lambda. H is what? Planck's constant, and that is a, you know who is Planck's, right. So, the German scientist who gave this constant to put at the relation, and that is the value is this. So, only photon 6.62 into 10 to the minus 34 joule second. Now, the only photon with energy that exactly matches with the energy difference, it is like this सीढ़ी पर चढ़ने जैसा, right. So, if you want to go from one step to another step, if you put it somewhere between, you will fall, right. You can only go to next step if you put this much leg space, right. So, similarly, if you want to excite a proton or nucleon or electron from one energy level to another energy level, you have to provide this energy, and that is come in quanta, right. Quanta means a fixed energy that comes like energy. So, when a molecule can absorb just light, the right amount of energy, like a climbing a staircase one step at a time, then only you reach it. अगर बीच में आधा अधूरा चढ़े, then you will fall, you cannot reach to next step. So, you require this amount of energy when a molecule is excited from this step to this step, and similarly in case of a spectroscopy, the right kind of energy is required for exciting a molecule, and that is given by this equation, Schrodinger's equation. So, a system or a molecule can adopt only a certain energy value, which are the eigenvalue of an Hamiltonian operator given by a simple Schrodinger equation, H psi equal to E psi. You know, this is the psi is a wave function, E is the energy, and H is a Hamiltonian. So, it only says, I do not want to go into detail, this is like your physics course, but it only says that this is a quantized, there is a observable value energy, eigenvalue is observable, and that has to be a fixed value that is come up. So, coming back to a spectroscopic case, our energy levels are like this stairs. This is a ground state, excited state, and all those, and ground state is the lowest energy state. All other state than the ground state will be called excited state, right. So, two state, like there is a one state here, if they will have same energy, that will be called degenerate state. If I want to excite a molecule from ground state to excited state, by shining the electromagnetic wave, we require energy which matches the energy gap between these two. Only then I can excite from the ground state to the excited state, right, and then molecule can go to the excited state to see any phenomena. Now, for the first class, I want to stop it here by summarizing what we discussed. So, we discussed spectroscopy is a discipline that is common in physics, chemistry, biology, and in life science. Only thing is that concept changes or the molecule of observation changes. Physicists are mostly in atomic, looking at the atomic spectroscopy. Chemist looks at molecular, but chemical molecular spectroscopy. Biologists look at the biomolecular spectroscopy, and life science you use this concept to do investigation, like I gave you example of blood detection, right. Now, we looked at that for any spectroscopy you require light source, a matter where this light is falling, then you detector, and then you processing unit, right. The light source, electromagnetic source are of two kind, wave like nature and particle like nature. Wave nature should be characterized by the wavelength, the frequency, and light of propagation. Like a particle like nature, the energy has to be quantized, and for doing any spectroscopy you require to provide the energy which can take from ground state to excited state. So, we will stop it here for today, and in next class we will continue our discussion how we can excite a molecule from ground state to excited state before we go to next concept. Thank you very much, and I look forward to see you in the next class.